All right, so if you haven't seen the intro to EAS, electrophilic aromatic substitution, and the mechanism for halogenation, then stop and check that out because these mechanisms are going to be much faster, and so that's because they're similar, right? So the first one we want to talk about is nitration. Then we'll get into sulfonation and Friedel-Crafts reactions. Okay, so nitration, sorry, if you add nitric acid and sulfuric acid, you'll get that benzene ring substituted with an NO2 group, so a nitro group. Pretty cool stuff. Nitro, as you've seen in previous videos, is trinitro with a methyl on there is trinitrotoluene, right? And so that's dynamite. So maybe we'll learn how to make that. I don't know. Sulfuric acid looks like this on the left, and then we've got our nitric acid that does the attacking of that sulfuric acid. You get protonated oxygen on there, and after that, what we've got here is something that looks like a pretty decent leaving group, right? So remember, we were doing what we can to kind of make the NO2 electrophile that we want. Okay, so of course, yeah, maybe we can protonate other things, but if we protonate other things, that's not going to get us to where we want. Okay, protonating that oxygen with the hydrogen on it already makes a water leaving group, which can then get forced out by that negatively charged oxygen, right? And then you get your NO2 positive, our electrophile with a positive charge on the nitrogen, so that's the electrophilic position. That's our E plus, right? And so now what we're looking at is benzene with E plus. We already know how to do this, right? So benzene attacks that nitrogen, and then we end up with an NO2 on there with at the sp3 hybridized carbon, a positively charged carbon in the ring. After we deprotonate that hydrogen with the conjugate base of sulfuric acid, we can reestablish aromaticity and we get our nitrobenzene. Okay, that's pretty much the same mechanism as before, right? Very straightforward. The base changed up, and then of course our electrophile changed up, and that's the tricky part, is remembering how to form that electrophile with sulfuric acid and nitric acid. But if the nitro group needs to come obviously from the nitric acid, right? Sulfonation, you know that you're going to add a sulfur containing group, right? And it's going to be that SO3 component. So you shouldn't get these two mixed up, and you should realize just sulfuric acid is going to protonate something in each of them. Okay, and then of course the SO3 is the source of our electrophile. So let's go ahead and label that guy in blue as well. So just like the HNO3 was protonated to get the NO2 electrophile, what can we do to the SO3 to get that positively charged or more susceptible to nucleophilic attack by the benzene ring? Well, we can also protonate that guy. And so what we're going to do is kind of use this pi bond to grab that proton, and then we get HSO4 minus, that's our conjugate base from sulfuric acid. And then we also have this guy right here with the positive charge on that sulfur group. Okay. All right, so now this guy, it represents our E plus in our general mechanism. So what we can do is draw benzene, draw our SO3H plus, and then have benzene attack it, right? So let's draw this guy out. We've got, can't forget our positive charge, and benzene now wants to attack that positive position, and we got a new sulfur compound on the benzene. And remember, just like in sulfuric acid, sulfur can have that expanded octet, and it really wants 12 electrons around it, and so that extra bond from the benzene is satisfying that positive charge. And so this is the structure of that intermediate. We reestablish aromaticity with removal of that proton from the conjugate base of the sulfuric acid, and that's our final product right there. This is the sulfonation product, and there's our positive, or our blue electrophilic SO3 source right there, right? That's where it all went. Okay, so the mechanisms again are all very similar, so we're just kind of cruising. There's more detail that's probably to be said about substituted benzene, or that doing EAS with substituted benzene, because it gets a little bit more tricky there. So those videos will be a little bit more detailed, but for now, let's just do Friedel crafts. Remember, the alkylation is basically a benzene ring with an alkyl chloride and aluminum chloride, and then it makes a benzene ring with an alkyl group on it, as well as HCl, of course. And then the acylation is basically a benzene taking this carbonyl compound. So this is an acid chloride, acyl chloride, with aluminum trichloride again, because that's our Lewis acid source. And then you add the carbonyl group to the benzene ring, making a new ketone. Okay, so that group right there is called an acyl group. That's why it's called Friedel-Crafts acylation. Okay, sorry, erase that, aka let's come over to the carbonyl group. So that carbonyl group right there, that's called an acyl chloride. It can also be called an acid chloride. And so when I refer to them, I usually refer to this guy as an acid chloride. Okay, just so you know, it's a carbonyl group with a chlorine attached to that carbonyl carbon. But they are the same thing. So if you're reading it or whatever, or writing, it's the same thing, and well understood on both sides. Okay. Alkylation mechanism. So this one can get tricky. So pay attention. It's generally the same process as you might expect, where the chlorine attacks the Lewis acid aluminum complex, right? You make this intermediate right here, this positively charged chlorine, obviously doesn't want to be positive, and so you can have something come along and attack that carbon, which would also be delta positive because it's next to a positively charged chlorine, which is more electronegative, and it kicks that out. It's a good leaving group now, right? Chlorine's already a decent leaving group, but it's even better now with that aluminum Lewis acid attached to it, okay? So that's really why these guys need to be present, because if it's going to be an easier leaving group, that's the first step in this mechanism, right? It's a two-step mechanism. The leaving group leaves, and you have the benzene carbocation intermediate, and then it gets deprotonated to reestablish aromaticity to make the final aromatic alkyl benzene, right? And so it's two steps. That first step is the rate determining step. It's higher in energy. It's really hard to force that leaving group to piece out if we're just using benzene. And so if we can make it easier to leave, we're lowering the energy of activation, and we do that with the aluminum chloride, okay? That Lewis acid, that's why that Lewis acid is so essential for these EAS reactions, okay? Let's take a look-see. This one's going to be a little bit different. Benzene attacked directly that alkyl group with the chlorine on it already, but since that's because that was a primary alkyl halide, this is a tertiary alkyl halide, and it can just leave and form a carbocation. That's very stable. Now, of course, this carbocation is susceptible to nucleophilic attack, right? We've seen lots of different carbocations that are floating around ready to be attacked by things, right? So since this is a stable carbocation, why not just form it in a variety of other ways, right? We know how to make carbocations, like we can use alcohols or we can use other leaving groups, right? And that's totally fair game, okay? So just be aware of the fact that if we can create a carbocation and we have a benzene present and we have something to kind of remove that proton in the end, then we can form a substituted benzene, okay? So that aluminum comes back, removes that proton to reestablish aromaticity, giving us this benzene chicken foot, right? Now it just looks kind of weird. It's a weird chicken. It's a one-legged chicken, y'all. Kind of laying down. Ooh, it looks like a drumstick with a little foot on there. Anyway, NaHCl, of course. So these reactions do form HCl, and so they're actually kind of yucky, I guess, to put it in, for lack of a better word. All right, so this one, All right, looks like the one we just did, right, with the ethyl chloride or the chloroethane. This, oh snap, Jess, you just did a 1,2 hydride shift to kick out that chlorine, the acid-base adduct, or a Lewis acid-base adduct. That's messed up, Jess. And then you form a secondary carbocation, which is totally fine to have. And this is definitely a thing, okay? So this chlorine attacks the Lewis acid, forming that acid-base adduct, and then the hydrogen can shift to make a more stable carbocation, okay? And then the same process goes from there. Benzene attacks, reestablish aromaticity, and you get your fancy looking isopropyl benzene, okay? So notice that if other than the chloroethane, you can always shift a hydrogen or a methyl group even to get a more stable carbocation. So you're actually never going to get a primary carbon attached to the benzene unless it's chloroethane, right? Unless it's that ethyl group, or unless you use a different method, okay? Now, of course, you can have a primary carbon on, kind of be attached to that benzene, but it's not going to be in this way because you can do shifts for days. Okay, so check this one out, right? Try and think about what would happen. We form this acid-base adduct. Boom. Now, okay, well, why don't you just peace out? Because you're a secondary carbocation. That's cool. That's totally fine. I'm good with that. Ready to go, ready to go. The benzene wants to come along and attack that, but he's not ready yet. Okay? Not ready at all. Because look at that. If we just take a look, that's a secondary carbocation, right? What if we did a 1,2 hydride shift to make a tertiary carbocation, which is more stable, much happier floating around like that, and still ready to be attacked by the benzene, okay? So you have to look out for these kinds of shifts. That's why it's really important to understand these mechanisms and the intermediates, okay? So once you do that, you get this new product formed right here. Of course, we can reestablish aromaticity in the same manner as before. So these reactions are pretty chill, pretty easy. They're not so bad if you understand the idea behind them, the goal, right? The Phoebe is super excited about this. She's like, wow, how did he do that? That's messed up. No, this is fun stuff. I like the ones that are puzzling, right? How did you get from there to there, right? You have to know the mechanism in order to understand that there is going to be a 1,2 hydride shift to get to that new product. Okay? Know your stuff. Regina Phalange would appreciate it. All right, so let's say I already referenced this before, but I'm just going to show you a couple examples, right? So if you add acid to an alkene, you get a carbocation, especially if it's a secondary carbocation, that's fine. And you can use that to attach to a benzene, right? Or if you have this tertiary alcohol here, add acid again, protonates the water, right? And then it leaves, forming a tertiary carbocation, okay? Now what would happen eventually, after a couple steps, benzene attacks, reestablish aromaticity, you get this cyclohexane attached to the benzene, right? And then, of course, another way to make the chicken foot benzene, tert-butyl-benzene. So keep that in mind. Anytime, any way you choose to make a carbocation, as long as it's stable, it can't rearrange, go for it. That you can make the carbocation however you want and then do electrophilic aromatic substitution with it. So that is the fun part of chemistry. Lots of different ways to do the same thing, okay? All right, so the acylation mechanism. This one's fancy as well because we're still going to do the same thing, right, where we form that Lewis acid base adduct because we still want to make this as low, the activation energy for this first step as low as possible. And of course, the Lewis acid is going to help with that because it's going to force this chlorine on the acid chloride to leave. Now, once that leaves, we're going to form something called an Acidium ion, okay? So it's a positively charged carbon, like carbonyl group, right? Now this positively charged carbonyl group, simmer down, iPad, is resonance stabilized. That's how we can justify this. So we can have a carbon-carbon or a carbon-oxygen triple bond now, still an acylium ion, and that carbon is definitely susceptible to nucleophilic attack by the benzene because the oxygen's more electronegative, right? It wants the electrons. So once the benzene attacks, then we're off to the races, right? Same story, same mechanism as before. So it attacks that acylium ion, kicks the extra pi electrons to the oxygen, so everybody's happy. Now we have a carbonyl group on there. Everything's kind of looking like normal, except we still need to reestablish the aromaticity, and we can do that with this aluminum over here. Just have that chlorine swoop on that proton to reestablish the aromaticity. Boom, boom, boom. Notice I keep drawing those hydrogens that are kind of involved in this mechanism. That's really important for you to do, just to keep track. And I don't know, it just helps me keep track of what's really going on, and also helps me keep track of my charges. Okay, so now I've got my new carbonyl compound. Cool, huh? And you can do tons of stuff with this now. So that's why this reaction is very important. Pretty sure Mr. Friedel and Mr. Crafts won a Nobel Prize for this, like probably back in the day, which was probably a Wednesday or something, I don't know. But per usual, the vinyl chloride and the aryl chloride, those guys they're not gonna work, right? They're not the sp3 carbons, and so they're not gonna react the same way. So here we go. The fun stuff. Y'all know I like intramolecular reactions by now, right? I hope you do. So intramolecular Friedel-Crafts acylation, super cool. You can do intramolecular Friedel-Crafts alkylation as well. But here's an example of the acylation. You got this acid chloride attached to the benzene ring with a long little chain there, and of course, same process, except now it's within one molecule, right? So we form this acid-base adduct. Let me move it over here, give us a little bit more room. So once that acid-base adduct forms, we can have that leave, and that forms the resonance stabilized acylium ion. Remember? There you go, acylium ion. And of course, the acid-base adduct, or it's not really an acid-base adduct anymore, it's just an aluminum tetrachloride anion. And we have resonance stabilization of this acylium ion, right? And that carbon, being next to the positively charged oxygen, is highly susceptible to nucleophilic attack. And so, blam, that's what happens. It attacks, restabilizes that charge on that oxygen, right? It's gone now, neutralized that charge. And here we go. What we want to do is kind of draw out red dots to trace out how big that ring is going to be, right? And we want to make sure that it's a ring size that's reasonable. So ideally it would be a 6-membered ring like it is here, because as we know from previous chapters, 6-membered rings are the most stable, more so than 5 or 7, for example, or 8 or whatever. And so once we form that ring, we reestablish aromaticity, and then we get this super cool fused ring structure with a ketone kind of nestled inside of it. Okay, that ketone is incorporated into the ring. Super cool stuff. Intramolecular reactions are always the coolest for me because it's difficult to trace out, right? It helps when you just kind of map them out with the red dots like I did. Count how many carbons, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Whatever. It just trace it out, mapped out your mechanism, and then just pay attention. So this right here is the process for making LSD. So this is, if you have the structure on the left, and you add aluminum chloride, and it does an intramolecular Friedel crafts, acylation to make this cool ring structure, which after a few more steps, of course, you get the structure on the right that I'm drawing, and that is LSD. So it just goes to show you how important carbon reactions that make carbon-carbon bonds can be. Obviously not just to make drugs, but pharmaceutical drugs that are actually more helpful than LSD perhaps. Things that fight HIV or cancer or I don't know. For whatever reason I can't think of diseases off the top of my head apparently. But anytime you can form a carbon-carbon bond, it's clutch. And so those reactions you definitely want to commit to your memory, your practice them a lot. Make sure you have those in your toolbox for sure. Okay, have fun. Bye.